One of the nice things about working with dynamic graphics is you get to come to talks with lots of toys. So, and then play with them during the talk. I think that the area of dynamic graphics, at least the modern era, started probably some 15 or 20 years ago with work by Tukey and Huber and Friedman and lots of other people. These early investigations were well out of the reach of most of us because of the investment required to get into the area. Investment both in terms of the cost of the equipment and in terms of the time that it takes to develop the expertise to do the required programming. Fortunately, today that's no longer the case. There are great public domain software programs for implementing dynamic graphics, and you can implement them on workstations as small as a Macintosh 2 computer that we're working with here. So the situation has changed over the last 15 years, and in particular, it's changed dramatically in the past 2 or 3 years. The early work on dynamic graphics, I think, can be characterized roughly in 2 areas. One area is how to plot. How do we actually make use of the computer to implement a lot of novel ideas? And the legacy that we're left with from these early investigations go under the names like spinning or rotation, animation, slicing, linking, brushing, touring, and on the list goes. A lot of great methods, a lot of novel ideas have been implemented. The ideas and how to do that, they're now known. The second area of investigation, and I think it's fair to say that this has been pursued naturally less than the first area, is in looking at raw data. How do we use dynamic graphical methods in essentially a strongly exploratory vein? Taking multivariate data, or perhaps univariate, putting on the screen and trying to understand the structure. I'm not interested in particular in those 2 areas. What I'm interested in doing is seeing what dynamic graphics can lend to more formal model-based analysis. And within the context of this workshop, linear models. So what I'm going to be doing today is talking about how to enhance, illuminate, and perhaps extend analyses based on linear models using dynamic graphics. I'm going to work in the context of one fairly straightforward question. When one thinks of a linear model or a regression model, one of the first plots that comes to mind is a plot of the ordinary residuals versus the fitted values. The structure of this plot and what one can do with it is certainly well known. It's been studied a lot, and it's offered as a first graphical or first diagnostic technique for regression in most elementary books on regression and most first exposures. So the issue then is, given this particular plot, how can we extend and enhance it using dynamic ideas? I'm going to concentrate on just 2 dynamic ideas in this talk. The first is rotation, and then later on we'll come to a second idea, animation. So let's first think about enhancing this plot through rotation. Now the plot that you're looking at is actually a 3-dimensional plot. You can't see the 3rd axis because it's coming straight out of the screen at you, but the label on the 3rd axis is 3 question marks. And the issue that we're addressing then is, what do we replace those question marks with? It's rather easier to tell you what not to replace the question marks with than to tell you what to replace them with. So let me tell you first of all what not to replace the question marks with. It didn't take us long to realize that spinning without anything on the axis, let me slow that down a bit, and maybe make them a bit bigger. Spinning with nothing on the out-of-page axis doesn't seem to do much good. We're working on a formal theorem and a proof for that, but the conclusion seems obvious. Well, there are other things that we might think about putting on that axis. We could think about putting case index, leverage, a distance measure, a column of x, and so on. None of these ideas, except for the and so on, seems to be very useful. Let's think about putting the leverage values on the axis, and let's start the plot spinning. Perhaps it would be a bit clearer if we get the rest of the lights out. Is that possible? And maybe if I... Is that better? There, I've selected the points and caused them to be highlighted, which gets rid of the depth queuing and makes depth a little bit harder to visualize, but the points themselves are clear. When we think of three-dimensional plots, one of the first things that I think is important to do is to look at structures where the three-dimensional point cloud gives you some sort of intrinsic information. There should be some pattern, some shapes that you're looking for in the three-dimensional point cloud. Otherwise, there doesn't seem to be much sense in spinning or in looking in three dimensions. Now, in this case, in this illustration, putting residuals on one axis, y hat on the other, and leverage values on the third axis doesn't give any intrinsic information in the three-dimensional point cloud. What we've done is taken an interesting two-dimensional object, the scatter plot, an interesting one-dimensional statistic, the leverage values, and we put them together in a three-dimensional plot. Well, 2 dimensions plus 1 dimension does not necessarily yield a useful three-dimensional plot, and I think that's what's important to take from this particular demonstration. That just because you have 3 variables, putting them in 3 space and trying to look at them in 3 dimensions isn't necessarily going to yield anything of worth, and that before you do these kinds of things, it's a good idea to know the kind of structure you're looking for in high-dimensional plots. Well, the issue then is, how can we continue? My hand-eye coordination takes a little bit to get used to here. There we go. When we think of the usual residual plot, what we've done is taken the residuals and used them as a vector that represents the entire airspace. We've taken the fitted values and used them as a vector to represent the entire estimation space. And all of the empirical evidence that we have in the theory suggests that these are 2 pretty good choices. Now that indicates that if we're going to think about something for the z-axis, perhaps we should think about choosing it in a purposeful way from the estimation space or from the airspace. And I'm going to put an additional constraint on that third choice, and I'm going to constrain that whatever values I put on the z-axis must be orthogonal to the residuals and must also be orthogonal to y hat. So I'm going to constrain the n vectors of plotted points to be orthogonal. Now, what that does is it automatically guarantees that you're going to maximize the dispersion in the plot. Any 2-dimensional projection of that plot that preserves the y-axis, if we think of the dispersion along the x-axis in a 2-dimensional projection, the minimum dispersion will be maximized if we choose our variables to be orthogonal. So subject to those 2 constraints, we're now going to consider what to put on the z-axis. I'm now going to turn on the other overhead, so you may want to shield your eyes momentarily. To decide what to put on the third axis, we have to have some sort of purpose in mind, and here's the context that we chose to work in. The general problem is going to be to understand how variables contribute to a regression model. So I'm going to take my regression or linear model and I'm going to partition it into 2 bits, x1 beta 1 and x2 beta 2. I'll call the first part the base variables, the second part the added variables. The general kinds of problems we're going to think about addressing with our choice for z, curvature in x2, influence and leverage, interactions between x1 and x2. Typical kinds of problems that you run into when you're looking at data from this kind of model.
The residuals are from the base variables only.
I beg your pardon?
Are the residuals from the base variables only?
No, the residual, well, I'll be coming to that in a moment. They can be either, to answer your question. Here's the basic approach. Again, we have the partition model repeated from the previous slide. That partitions y into p1y plus p2.1y plus qy, where p1 is the projection operator for x1, p is the projection operator for the full column space of x, and p2.1 is the projection operator for the part of x2 that's orthogonal to x1. So with that partition, what we're going to put on the 3 axes is indicated inside the box. On the out-of-page axis, abbreviated OOP, we're going to put y hat 1, the fitted values from the regression of y on x1 alone. On the horizontal axis, we're going to put y hat 2.1, the fitted values from the regression of part of x2 that's orthogonal to x1. And on the vertical axis, we are going to put the residuals E from the full regression. So we now have defined the three axes. These things are, of course, orthogonal, and they fall within the framework that I mentioned previously.
What does OLP stand for?
Out of page. We started doing this before we had computers, and then we were bringing things out of a page instead of out of the screen. Now, it turns out that that structure is rather rich. It gives us a lot of things to look at in the context of a three-dimensional plot. Let's first of all start with what we will see on the computer screen prior to rotation, just as we did in the illustration prior to rotating and seeing the question mark axis. So that's indicated by red. That's no rotation, and it will be a plot of E versus y hat 2.1. Now, it turns out that this plot is a fairly standard object. It's called a detrended added variable plot, abbreviated DAVP. There's a lot written about this in the literature. You can tell things about leverage. You can tell things about curvature in the model, influence. It gives a lot of nice information relative to bringing x2 into the model. So the initial two-dimensional projection that we see is useful in itself. Now, if we think about purple next, and we rotate around the vertical axis through an angle of theta, and what will be plotted, what we will see with the projection that's left is a plot of E versus sine theta y hat 1 plus cosine theta y hat 2. That's also a detrended added variable plot for some vector x in the column space of x. So as we rotate, every single two-dimensional projection that we see is also a standard graphical construction for these kinds of problems. Now, if we next think of green, and we rotate around the vertical axis through a specific angle, pi over 4, then what we see is the standard plot of the residuals versus the fitted values for the full model. And that's indicated by green. So that's, and I pushed that up just a touch too high. That's indicated by green. Then we will have a plot of E versus y hat. Now, thinking about blue, if we rotate around the out-of-page axis through an angle of pi over 4, then rotate around the vertical axis through an angle of pi over 2, you will be left with the standard residual plot for the subset model, E1 versus y hat 1. So we automatically have three interesting two-dimensional projections in the plot, standard two-dimensional projections, in addition to the purple that give us detrended added variable plots for other vectors in the column space of x. Now, other rotations are not residual plots in general. However, there is a particular path that takes us from the subset model, the blue plane, and rotates to the green plane, so that every two-dimensional projection we see while moving through that path is in fact a plot of the residuals versus fitted values for some analysis. And that final thing looks like this. The way that goes is the following. These are called Aries plots, A-R-E-S, Aries plots and Aries rotation. Aries is an acronym that stands for adding regressors smoothly. So here's the problem we have in front of us. We want to extract more information from this plot, more information than the rotation around the vertical axis and the three two-dimensional projections we've identified. We want to do that by rotating from the red plane to the blue plane and back again. And here's how we're going to accomplish that. We're going to accomplish that by using ridge regression estimates. So I rewrite my model as it's indicated there, and I get a ridge estimate beta hat lambda for a ridge parameter lambda. What I have on the screen is for the special case when x2 is a single column vector. This is for simplicity only. There's absolutely no restriction that says you must have it in this way. So for a single column vector x2, there's beta hat lambda, lambda referring only to beta 2 part. Now, from that ridge regression, we have residuals and fitted values as indicated here. They're linear combinations of the things we put on the axes. The coefficients being 1 in each case and lambda over lambda plus 1 or 1 over lambda plus 1. Now if lambda is equal to 0, then what we have is the residuals versus fitted values for the full model. If lambda goes to infinity, we get the subset model. Looking at the bottom 3 lines, if we rotate around the out-of-page axis through an angle of theta, what we're left with on the vertical axis is proportional to what is indicated there. If we rotate around the vertical axis through an angle of theta, what's left on the horizontal axis is proportional to what's indicated there. We compare the trigonometric functions, the tangent and the cotangent, to the expressions for the residuals and fitted values from the ridge regression. You can see that as long as we perform our rotation using the equation, using the restriction given in the last equation on the slide, the tangent of eta of theta has got to be equal to 1 minus the cotangent of theta. As long as we employ that restriction, then as we rotate, we get ridge regressions. And what we get more specifically are plots of residuals versus fitted values from a ridge regression with an index parameter lambda. So that's another benefit from these 3-dimensional plots. Now at this point, we're almost ready to see the consequences of this on the screen. But before I can, there's one more detail that I've got to tell you about. And that detail is scaling. There are 2 kinds of scalings that we can think of when we use a computer. One is called AAA scaling, and it's implicitly what I've been talking about, what I was talking about on the previous slide. And the other is Avc scaling. The difference between these 2 is the following. The computer screen has a fixed plot area. And obviously we'd like to be able to make use of that full area. But to do that, it means we usually have to multiply or scale each of the plotted variables by a different constant to fill the computer screen, since the computer screen is a fixed area. Now, the minute we do that, that's called ABC scaling. That's indicated on the top half of the slide. The minute we do that, all of the pi over 4 angles, all of the structure of the plot changes. All of the angles, everything that we need to do, everything we have to keep track of in terms of these rotations, now becomes a function of the scale factors A, B, and C. That's what you need to do to enhance the resolution in the plot. On the other hand, those scale factors distort relative magnitudes. It can appear, for example, that the residuals from the subset model are much smaller than the residuals from the full model because of the scaling problems. So for there, you need fixed scaling so that you can compare relative magnitudes. And the fixed scaling is what we were essentially talking about on the previous slide. The most we can do with fixed scaling is to fill up one axis of the plot fill up the allowable plotting area on one axis, and then the other 2 are just what they have to be. Now, in effect, what's happening with scaling is we're really changing the basis for the subspace. Instead of working in a basis which is the natural basis, the identity basis in terms of E, y hat 2.1 and y hat 1, we're scaling these and in effect changing the basis. So from plot 1 to plot 2, we're changing the basis. Actually, when I started doing this, it didn't take long before I got an entirely new feeling for things like orthogonal matrices, projections, and bases, because they all have a particularly devastating consequence if not used properly in these things. Here is one consequence of scaling. If we look at what's on the vertical axis, E over B, and look at what's on the horizontal, and look at the E over the square root of A squared plus B squared, what's really on the diagonal axis, then the ratio of the residuals is going to be multiplied by a constant which is the root of 1 plus A over B squared. And that's the distortion caused by scaling. You're not looking, when you look at the plot, you're not looking at relative magnitudes, you're looking at relative magnitudes multiplied by a constant that typically you don't know. Most computer software implements ABC scaling, And so if you do this kind of thing or look at any relative magnitudes through rotation, you can be off by those kinds of scale factors, and that can be very dramatic. Even in AAA scaling, you're off by a square root of 2 when you think about these plots. And this is what we've come to think of as the projection distortion of relative magnitudes whenever you're using computer projections.
Is using different scaling for different data plots?
Yes, well,
It's the same scaling always. Well, there's always one scaling anyway.
one or the other, yeah. All right, that is the end of that. Let's now look at some examples. These examples are intended to illustrate the previous discussion, so there will be no new material per se. We're now going to choose the base model. This is a set of constructed data. I made it up. So here's the base model. We'll put 3 variables, x0, x1, and x2 in the base model. Incidentally, this is written in Lisp, and in Lisp you always start counting at 0. So x0 in this case does not mean a constant. It actually means the first x. So there are 4 x's. Those will go in the base model. There's only one left. We'll put that as the added variable. The syntax follows exactly what I was saying in the talk. And there's our 3-dimensional plot. The default option in the 3-dimensional plot is fixed scaling. So for the purposes of illustration, let's first, the default option is variable scaling, Avc scaling. For the purposes of illustration, let's first change that to fixed scaling. So that's AAA scaling. You can see already how the plot's characteristics change dramatically. That plot that we're looking at isn't terribly useful because of the way it's scaled, but it should serve as a useful demonstration. Now, let's rotate to y hat. So now we have a rotation of 45 degrees around the vertical axis. That's now a plot of the residuals versus the fitted values for the full model. We can go back home. And as you'll recall, that's a detrended added variable plot for adding x3 in this case after x0, x1, and x2. Let's again go to y hat. Now, one of the consequences of scaling, changing bases, can have dramatic consequences. Let's take a look at this plot, and let's see what happens when I go to variable scaling. Characteristics of the plot changes drastically. And again, that's an illustration of the importance of paying careful attention to the basis that the computer is using to construct this plot. Let's rotate to E1, and by E1 I mean the plot of the residuals E1 versus y hat 1. So that's now the subset model. And again, if we change scaling, we see rather dramatic consequences. Again, that plot is a pretty clear indication that whatever is happening, it seems like there's not a constant variance in the direction of y hat 1. So let's go back to fixed scaling, and let's now think about Aries rotation. We're now going to rotate systematically to the residuals versus fitted values for the full model, and we will now come back. Every time I click on Aries rotation, it goes to the previous one. So now I can go back and forth as much as I like. Okay. Let's now pass to Avc scaling. Let's go home and rotate to y hat. Rotate to E1. Now, when we rotate to E1 in this case, the plot's going to change very little because of the nature of the scaling. Just a bit. Rotate, now do the Aries rotation back. Let's go back home. And let me now spin around the vertical axis. And there's supposed to be a lesson here, or not a lesson, but a demonstration. So I'll give you a second or two to see if you can see the shape that exists there. Anyone able to discern the shape? Yes, it's a saddle shape.
It's a saddle shape.
It's a saddle shape. It's much clearer on the computer screen. There's a little a little lag here. But if you look at it long enough, I think you can get the feeling of a saddle shape. What does a saddle shape tell you? Well, a saddle shape, it turns out, characterizes the presence of an interaction. Whenever you see a saddle shape in a three-dimensional plot of this form, it means there is an interaction between the base variables and the atom variables. So in this case, we do have a particular intrinsic characteristic of a three-dimensional plot that indicates something is needed in the model. And in this case, it indicates that an interaction is needed. Now, for the next demonstration, you can see those sorts of interactions with many fewer points. Let's look at a data set on cloud seeding. There are several covariates measured during the course of this cloud seeding experiment, things like the percent cloud cover, seeding suitability criterion, the day in which the experiment was conducted or the observation was taken. We'll take all those covariates and we'll put those in the base model. And we'll leave the one critical variable, the action, whether or not the cloud was seeded, an indicator variable, as the atom variable. And what we're going to be looking at for are interactions between the action and the rest of the variables. If we now spin around the vertical axis, you don't get the full saddle picture here. But what you see are two sets of points that look like they lie on the side of a trough. Again, you've gotten two bits of the saddle. The stirrups, if you will, are sort of missing. But again, this is an indication of an interaction. And if you carry on the analysis now in the more traditional form, looking for interactions, you find that indeed there are strong interactions between action and other variables in the base model. Here's another set of data, on the amount of cotton dye stuffs produced. I took this from Davies' book. There are three chemicals compose the dye, abbreviated C, N, and V. We'll put C and N in the base model. We'll put V as the single added variable. There we have our plot again. The original plot, the initial plot is a detrended added variable plot. There's nothing much that that plot shows. Let's rotate to y hat. There is nothing much that this plot shows. Let's now rotate to E1. So now we have residuals versus fitted values from the subset model. And in the subset model, it looks like we have strong curvature. Very, very strong indication of curvature in that set of data for the subset model. If we now perform an Aries rotation, going from the subset model to the full model, we see the curvature gradually disappear. If we go back, we see the curvature reappear and disappear between the full and the subset models. The idea behind this demonstration, if we now go back home and spin around the vertical axis, the idea behind this demonstration is that what's happened to the curvature is simply move from the critical y hat direction in the full model to a different direction in the subspace, but the curvature is nonetheless there. So the curvature still exists in a subspace of the column space of X. We've succeeded in at least getting close to that subspace using this two-dimensional subspace of the column space of X, spanned by y1 and y2.1. And again, we see the curvature. So another useful feature of these plots is for looking at plots of E versus many directions in the column space of X at once. This is a set of data on the lifetime of tool bits that are used in a lathe. There are two. This is a designed experiment. There are two design variables: the speed of the lathe, how fast the thing is turning, and the feed rate, how fast the workpiece is being pushed into the drill bit. The response is the log of the lifetime. So there's the feed rate. The point of this demonstration is again to reinforce the idea of how important it is to pay attention to the basis or the scaling that's being used in whatever program you're dealing with. What I want to do is concentrate on one issue in this plot. Let's rotate to y hat 1 first of all, and then let's rotate to E1. We now have a plot of the residuals versus fitted values for the subset model. We're now going to perform Aries rotations, a couple of them, and what I would like you to try and do is get an intuitive feeling looking at the visual representation of the plot, an intuitive feeling for how the magnitudes of the residuals change when you go between the subset and the full model. So now we're at the subset model. Let's go perform an Aries rotation to the full model. My impression when I look at that is that on average the magnitude of the residuals don't change much between the subset and the full model. That's a consequence of scaling. If we pass to fixed scaling, so we have a better chance of looking at relative magnitudes, and then perform Aries rotations, we get a much better feeling, I think, of how the residuals are changing, and it's clear that adding feed to the model is reducing sort of the average size of the residuals much more than it appeared in the previous demonstration with Avc Scaling. In fact, that plot we found to be so useful that we decided to take it out of 3 dimensions and put it in 2 dimensions. And we did that so we could get away from the projection distortion that I was mentioning previously. So the next thing we're going to do is take another look at exactly what we've seen, only we're going to look at it not in 3 dimensions, but in 2 dimensions. So we're first of all going to choose the base predictor model, which consists of just feed, and then feed, that's the value of lambda in the ridge setup. Now we see exactly how the residuals change, exactly how the plot changes as we add feed to the model. It's much clearer here what the effect of adding feed is. Now taking feed out of the model, and we're now putting feed back into the model. Now it looks like when we look at this particular graph, we have the center points of the design region lying below the rest, so maybe fitting a different sort of model to this setup would be helpful. And let's do that next if I can get the cursor over here to close this plot. There we go. Let's look at a full quadratic in the 2 variables. Let's, in the base model, put feed and speed. Okay. And as the added variables, we'll put quadratics and the interaction. The variables are going to be added to the model in the order that I clicked on them. So in the order that they're given in the box, they'll be added. Speed squared, feed squared, and then the interaction, if I clicked in a different order, the variables would have been added in a different order. We can add them as a group or we can add them sequentially, so let's add them sequentially. So now we have a model, feed speed as the base model. We're going to add speed squared, feed squared, and the interaction. One right after the other. Now, speed squared is in the model. Feed squared is in, and we're now adding the interaction. The value of lambda over here doesn't exactly mean the value of lambda. If I back off just a bit, 2.9 means we've added 2 variables and 0.9 of the 3rd variable. So we've added those 2, and the value of lambda for the interaction is 0.9. So let's back off. And what you see is that the interaction doesn't change much. Doesn't change the residual plot much, but now the quadratics do change substantially. Okay, once again, you can play these. It usually takes 2 or 3 times playing them back and forth before you get a reasonable feeling of what these things look like. Again, when we hit the interaction, the points bounce around a bit, but they don't matter. They don't move much. One final illustration of that. Let's look at a different set of data on rats. 3 explanatory variables, body weight, liver weight, and the amount of dose that a rat was given. The response is the amount of dose that ended up in the liver of the rat. We'll add dose. And I think what I'm going to do is go directly to an Aries plot. We'll put body weight and liver weight in the base model. We'll put dose, the critical variable, as an added variable. Change the point sizes there. Now the question is, what does this mean? Again, I'll play it back. We're now taking dose out of the model. And again, we'll put dose into the model. You see what's happening? Only one point is changing. Everything else is just bouncing around a little bit. And that's a graphical illustration of the effects of a single influential observation on dose. And that's what influential observations look like in these plots. They tend to move much more than the rest of the variables, and it's clear what's happening. The line is being bent to fit one particular point, that point which happens to be case 3, and that's a very influential point in this particular data set. I've lost track of time since we started.
Yes, roughly, I'll wait for me. Another 3 minutes, that's fine. So.
Another 3 minutes?
Yeah.
Okay. Another 3 minutes.
5 minutes.
5 minutes, 10 minutes? Okay, I understand.
You can go to 30 minutes.
I can go to 30 minutes
Yeah.
if I like.
If you like.
And I can use that you for my authority.
Right.
Okay. We're now working on extending this to many dimensions. 4, 5, 6, a lot of dimensions. The theory is easy to extend, but the graphical methodology is not. And what we've been working with is how to use Turing notions to extend this methodology. The idea behind Turing roughly is as follows. What we have on the screen is a 4-dimensional plot. You can only see one 2-dimensional projection, but there are actually 4 axes there. What I'm going to do to look at this set of 4-dimensional data, incidentally, this is not regression data. This is simply multivariate data. The idea here is more of an exploratory vein, just to ask what's the structure of this data set. So what I'm going to do is pick a random vector in the plot, a random 4-dimensional vector in the plot. Then I'll pick another one. I'll rotate from the first to the second. Then I'll pick a third random vector, rotate to the third, pick the fourth, rotate to the fourth, and continue random rotations in that fashion to see if we can get an intuitive feeling for what this set of data looks like. So we're rotating in 4 dimensions, looking at a sequence of 2-dimensional projections as we rotate. This is the set of data that came from a cancer study at Los Alamos National Laboratories. You have to be patient when you look at these things. It takes a while. I think you've probably already gotten the idea that there are clusters here. problem that they wanted to solve was in fact a cluster analysis problem. And there you can just make out 5 clusters that are present in that set of data. And the answer, as confirmed by numerical cluster analysis, is that there are 5 clusters, and fortunately there is a 2-dimensional projection of that 4-dimensional plot that serves to distinguish those 5 clusters, and we've just seen it several different times. You can also, as I mentioned, this is looking at a sequence of 2-dimensional projections of a 4-dimensional plot. You can also look at a sequence of 3-dimensional projections of a 4-dimensional plot. And you look at that by taking the screen plot and rotating it while you're rotating in 4 dimensions. So you're doing 2 simultaneous sets of rotations in 4 dimensions and a rotation in 3 dimensions. And you do that by setting the screen rotation angle, which is indicated there. And I think I've just probably taken 3 minutes, so thank you.